In the first two lectures, on Wednesday and Thursday, we studied the range of neutrino masses from basically several GeV or so, all the way down to about a few electron volts. And just to remind you very quickly, we had a direct experimental limit for nu tau, nu mu, nu e. We then had a discussion of cosmological limit, and we found out that cosmology is giving us a very strong limit for stable neutrinos, which have to be below 20 or 50 electron volt. It also gives us limits for unstable neutrinos, and unstable neutrinos could have any mass provided their lifetime is short enough. But we also then analyze the possible lifetimes of neutrinos from the point of view of particle physics, and we found out that neutrinos from the particle physics point of view can also have constraints relating their masses and their lifetimes, but those constraints go in the opposite direction to the cosmological constraints. In other words, the cosmological constraints say, give me a mass, and then the lifetime has to be shorter than something. The particle physics constraints say, give me a mass, and then the lifetime has to be longer than something. And the question was whether by combining these two limits, we can exclude certain areas. And the final example I showed yesterday, this is not the only example, but the final example I showed is the example of the most dangerous case, the case in which it is most likely to have a fast decay, and that is the decay of a heavy neutrino to a muon. And even in that case, from the particle physics point of view, you have to be above the orange line. From the cosmology point of view, you have to be to the left of the red line. And from the direct measurements, you have to be below the green line. So for the tau-neutrino, you must be in this little corner. And for the mu-neutrino, you only have this very, very tiny, practically vanishing corner here. We also said that even these corners can be eliminated by a somewhat more complicated argument related to primordial nucleosynthesis. And therefore, we found a beautiful relationship combining cosmology, astrophysics, and particle physics that essentially says that it is very unlikely that we will have any neutrinos above this line here, the line of 20 to 50 electron volt. It is not 100% excluded, but it is extremely unlikely, and I will come back to this issue later. And that brought us to the question, how do we probe neutrino masses below that line in the range of electron volts, or possibly much below that, perhaps milli-electron volt or micro-electron volt? And the answer was only by neutrino oscillations. And neutrino oscillations are possible because the three different neutrinos, nu e, nu mu, nu tau, are not necessarily the three eigenstates of mass. The three physical light neutrinos, which are mass eigenstates, are in principle nu1, nu2, nu3, and each one of those is a linear combination of nu e, nu mu, nu tau with the usual mixing matrix, which is very similar to the quark mixing matrix, except we don't have any idea what the angles are. And that leads to the possibility of neutrino mixing and neutrino oscillations. Now, I'm not going to give now a whole review of the formalism of neutrino oscillation. This can be found in many, many textbooks, and it is very, very similar to the formalism of k short, k long oscillations. But I will just remind you the main features of oscillation in vacuum and oscillation in matter. And just in order to remind you, we will consider only two generations, just neutrino electron, neutrino muon for pedagogical reasons, although, as you know, perhaps the most important neutrino for the purpose of our discussion may be actually the third one, the tau-neutrino. But just for the pedagogical purposes, let us imagine we have only two neutrinos. And then nu e and nu mu are linear combination of nu1, nu2, which are the mass eigenstates, with coefficients which are cosine, sine, minus sine, and cosine. And this is the leptonic analog of the Cabibbo angle. This is the mixing angle. But then, because nu1 and nu2 have different masses, and therefore if you have a neutrino beam with a given momentum, the two neutrinos of different masses will have different energy. The time development of the component nu e and the time development of the component nu mu will depend on the e to the minus I e1t and e to the minus I e2t, and therefore the proportion of nu1 and nu2 in the beam will change, and that is, of course, the oscillation effect. You can rewrite this equation by rearranging it, and it's an exercise more or less of a high school level to do this, by writing a differential equation for nu electron and nu mu as a function of time, and this time development, the time derivative of the time development, is related to the time development itself by this simple matrix. We had sine and cosine of 2 theta, and it has here delta E, which is nothing but E1 minus E2. And delta E, E1 minus E2, is essentially delta m squared over twice the momentum. So eventually you immediately see that the possibility of mixing depends on having a delta m squared not equal to 0. That is obvious. You can have this oscillation only if the two neutrino masses are different. And it also depends on having sine theta being not equal to 0, because otherwise each neutrino will remain itself and will never oscillate to the other one. So everything you do here has to depend on these two parameters being non-vanishing, delta m squared and sine 2 theta. And it is very clear from this analysis that the smaller theta is and the smaller delta m squared is, the smaller the oscillations are, because they have to vanish in the limit that delta m squared is equal to 0 and in the limit that theta is equal to 0. And you have the famous formula that, for instance, the probability of starting with an electron-neutrino beam and ending with a mu-neutrino beam is proportional on one hand to sine squared 2 theta, where theta is the E-mu mixing angle, and on the other hand to sine square of an argument which involves delta m squared, but also involved L over E, where L is the distance over which the oscillation took place, and E is the energy of the beam. And the units could be either L in meters and E in MeV, or L in kilometers and E in GeV, which of course gives you the same ratio. And 1.27 is just the coefficient that you get from the conversions of units from one unit system to another, from meters to GeV, etc. Now, that means if you consider this to be of order 1, and incidentally, and delta m squared are in electron volt. So if you do an experiment with an MEV beam at a distance of 1 meter, which is a typical nuclear reactor experiment, you can probe roughly the range of 1 electron volt. And when you do an accelerator experiment, which will typically have GeV beams and 1 kilometer distances, you are again probing roughly the same area, roughly the same range of 1 electron volt. This is oscillations in vacuum. A completely different situation occurs in matter. Because in matter, when you have neutrino beams propagating in matter, you have exactly the same situation. You have different energies, and the neutrino of one kind can oscillate to the other kind. But there's another thing which is changing, which is making a big difference between the two neutrinos, and that is the electron neutrino, and only the electron neutrino, can have one interaction in matter which the mu-neutrino and the tau-neutrino cannot have. And that is the electron neutrino can interact with electrons in matter by W exchange and have essentially a charge exchange interaction. This is something, of course, that the mu-neutrino cannot do, because you cannot have mu-neutrino hitting an electron, exchanging a W, and becoming an electron. And therefore, when you are at energies where you can make an electron and you cannot make a muon, you have a completely different cross-section for the electron neutrino, and therefore the mean free path, if you wish, or the absorption cross-section, or the interaction probability of an electron neutrino is much higher than a mu-neutrino. And this matrix, which has here in vacuum only terms which are related to the mass difference and to the angles, is changed by one extra term, which is A here, and instead of what you have here, just in the 1-1 position, in the electron-neutrino position, you have one extra term, which is proportional to the strength of the weak interaction, and most importantly, to the density of electrons in the medium through which you go. And that, of course, will change the situation. And again, I'm not going to review the whole formalism, but we would like to consider just one position which immediately explains to us how seriously the situation can change. Imagine a case in which A is exactly equal to 2 delta E cosine 2 theta. In other words, the mass difference of the neutrinos and the mixing angle of the neutrinos are such that the density of the material through which the neutrino propagate happen to be exactly equal, namely to exactly satisfy this relationship. In that case, A minus delta E cosine 2 theta and delta E cosine 2 theta are the same, and the two matrix elements in the main diagonal become equal. So you have here a matrix which has the form XX, YY. And such a matrix, when you look at it carefully, the XX, or anything proportional to the unit matrix in the main diagonal in such a differential equation, is nothing but an overall phase which doesn't change any of the physics. And you end up essentially having a revised differential equation which is proportional to a matrix of the form 1, 1 in the off diagonal and 0, 0 in the diagonal, which means that you have complete full mixing. In such a crazy condition, if you could have a uniform piece of matter in which the electron density is exactly obeying this relationship, what will happen is that all the electron neutrinos will become mu-neutrinos and all the mu-neutrinos become electron neutrino. Now this is of course a crazy situation, it never happens. Why should any piece of matter will be exactly with that density? But that gives you the simple arithmetics of the phenomenon. This is essentially resonance oscillation. You reach a situation of a resonance. In real life, for instance in the sun, what you have is density which changes. In the outside of the sun there is smaller density, in the center of the sun there is higher density, and as you go through the density change, you are possibly or very likely reaching a situation on the way in which you hit that density in which this transition can occur. And at that point you will have very strong oscillations, provided that sine 2 theta is not 0. But it doesn't matter anymore whether sine 2 theta is small or large. So the whole beauty of oscillations in matter, as discovered by Mikheyev, Smirnov, and Wolfenstein, the whole beauty of it is that you can have very significant oscillations if you hit this resonance position, and the only requirement is that your delta m square is not 0 and your sine 2 theta is not 0. But for a small theta, you can still have very substantial oscillations because they are enhanced by this effect. Now, in principle, oscillations in matter can happen not only in the sun, they can happen in the earth, they can happen in the atmosphere, they can happen in all kinds of places, but you need to have a very high density in order for this resonance effect to happen, and that is why the sun, or for that matter, stars, are good places for observing this effect. So when we are trying to probe neutrino masses and mixing angles, we would like to do a variety of neutrino oscillation experiments, and here is a complete list of the types of experiment that we have. One type is to do reactor experiments in which we have a length of a meter, typically, and an energy of MeV. The neutrino of the reactor is always an electron neutrino, and what you simply measure is how many of them remain in the beam or how many of them disappear. And you don't have enough energy to create a muon, and therefore you don't know if you are making mu-neutrinos or tau-neutrinos, but you can count how many electron neutrinos appear or disappear, and that is one type of experiment. The second type of experiment is in accelerators, where you have a mu-neutrino beam, and there you can either do a disappearance experiment, in other words, count how many mu-neutrino remain in the beam or how many disappeared after a certain distance, but you can also search for the other type of neutrino appearing in the beam. And I'm not getting now into the experimental problems of this. Obviously, for instance, if you're discovering an electron neutrino which appeared, you have to worry about the typical 1% contamination of electron neutrino in a standard mu-neutrino beam and things of that sort. But let us ignore for the moment the realities of life and just talk about the principle. The principle is that you start with a mu-neutrino beam and you search for electron neutrino and tau-neutrino through their interactions. In other words, neutrinos producing a single electron or a single tau. The third type of experiment, which is quite interesting, is oscillations in the atmosphere. And here, there's the following situation. In cosmic rays, you have a variety of particles which decay, producing muons, for instance, pions or kaons. Whenever a pion decay, it produces a muon and a mu-neutrino, and then the muon decay, producing one mu-neutrino and one electron neutrino. So in this simple chain, altogether, there are two mu-neutrinos and one electron neutrino. So in these very childish, naive calculations, the number of mu-neutrinos coming from the atmosphere, coming from essentially secondary decays of cosmic radiation, the number of mu-neutrinos should be twice the number of electron neutrino. And you can set up an underground experiment such as Kamiokande or IMB, which are not designed for that purpose, but this is a byproduct. And you can see if you have twice as many mu-neutrino as you have electron-neutrino, and both of these experiments did not find twice as many. What they found is roughly, crudely speaking, comparable number of mu-neutrinos and electron-neutrino. Now, I'm obviously oversimplifying because there's Monte Carlo to do on the detector and Monte Carlo to do on the atmospheric creation, and it is not 2 to 1, but it is only approximately 2 to 1. And there's many complicated considerations, but the principle of the experiment is that. And if you find deviations from this 2 to 1 after all experimental effects are taken into account, this may be indication that there were some oscillations on the way. The next method is not really oscillation, but is mixing. You look at any decay involving a neutrino. It could be ordinary beta decay or K decay or pi decay. And in such decays, you know what should be the momentum spectrum of the outgoing particle if there's only one type of neutrino. For instance, in pi decay, the muon should always come exactly with the same energy if the neutrino always have the same mass. But if there is neutrino mixing and the muon comes 99% of the time with one type of neutrino, let us say nu2, and 1% of the time with some nu1, then 1% of the time the muon will come out of this decay with the wrong momentum. And in that way you can find mixing. And by not observing such things, you can put important limit on mixing. That incidentally, in principle, not in K decay, pi decay, but in ordinary beta decay, is how the famous or infamous 17 keV neutrino was discovered, by having a deviation from the normal expected spectrum of masses in a normal beta decay, and that is why such a neutrino was suspected. And last but not least, solar neutrinos. We already explained. Neutrinos coming from the center of the sun can go through a region of resonance, and although the original neutrino is an electron neutrino, it has a high probability of converting to mu-neutrino and coming to Earth. The entire world data on neutrino oscillations of all of these kinds can be described on this graph, which has here, as usual, the neutrino mass, again from microelectron volt to GeV. And here we have sine squared 2 theta, because you have seen that in all of these neutrino oscillations and mixing, sine squared 2 theta is always the relevant quantity. So instead of plotting theta or sine theta, we always plot sine squared 2 theta. And here is the compendium of the world data. On mu-e oscillations, you have this red curve, which is an exclusion curve, and therefore things have to be to the left or below this. This comes from accelerator experiments. This comes from reactor experiments. The blue curve is mu tau, which we will discuss in detail later. The green curve is e tau. The 17 keV neutrino, if it existed, would have been here. This is 17 keV, and that is the amount of mixing that was allegedly observed in the original experiment. And you immediately see from that that it could not be an mu mixing because it is inside the excluded region. Therefore, it can only be e tau. And therefore, the 17 keV neutrino, if it existed, could only be a tau neutrino. And it would have to be a tau neutrino with exactly this type of mixing angle, etc. But we know that it doesn't exist. The atmospheric neutrinos, if you take the result as positive evidence for oscillations, point to something here, which means masses below 1/10 of an electron volt and mixing angles which are very large. And the solar neutrinos, to which we now turn, will eventually lead us to the range between 1 millielectron volt and 10 millielectron volt, as I will show you in a minute. We will come back several times to this picture. For convenience, I just drew here the positions of the 3 mixing angles of the quark sector, which need not be related, it need not be equal to the neutrino mixing angles, but just to guide your eyes. This is sine square of 2 theta of the Cabibbo angle. This is sine square of 2 theta of the VCB, the bottom decay to charm angle, and this is sine square of 2 theta of the 1,3, the VUB angle, just for reference. For solar neutrinos, the situation is very different. We have these 4 experiments that publish results and several additional exciting experiments under preparation. And in that case, what we have are the following results. In every case, the experiment is limited by some minimum energy, which is listed here. The original Davis home-stake mine experiment is only for energies above 0.8 MeV. The Kamiokande experiment is above 7.5. And the gallium experiment, SAGE and GALEX, are probing much lower energy, and they're probing the main nuclear transitions in the sun, and they go all the way down to 0.23 MeV. The way in which the experiment is done is very well known, and here are the nuclear reactions, the neutrino interactions which are observed experimentally. And for every such experiment, there's a prediction of the standard solar model, SSM, and the experimental result. And the famous results for 25 years of running for the Davis experiment is a ratio of roughly 1:4, but with large uncertainty here. The Kamiokande result is about 1:2, but at a different energy. The GALEX result is a result of about 60% with some large errors. And the SAGE results went through changes from 90 to 91, but eventually settled on something consistent with GALEX. So we really have 1, 2, 3 experiments and a fourth one which is consistent with it. And here I write an average of the 2 years, but the 2 years are barely consistent with each other. So we will concentrate on Davis, Kamiokande, and GALEX. And these are the 3 main experiments. And the fact that the ratios are not the same is perfectly reasonable, simply because they are probing different energy ranges. For each of these experiments, you can analyze it. First of all, you can analyze it in terms of the MSW effect, oscillations in matter. And by taking the experimental result, its ratio to the theoretical standard solar model, and comparing it to the explicit known formula for neutrino oscillation, you can find a positive region in the plot of mass versus sine squared 2 theta. Positive region if you say that the observed effect is entirely due to neutrino oscillations in matter. If you do that exercise for the home-stake mine experiments, the old chlorine 37 Davis experiment, you find that the allowed region is inside this blue thing. This is excluded, and outside is excluded. This is the allowed region, which means that you can have practically any angle you wish. If the mass squared, this is now delta m squared, if the mass squared is here, you can have a large range of masses if the angle is very large, almost full mixing, and you also have this diagonal area. Delta m squared is the difference between m1 squared and m2 squared, the masses of the 2 neutrinos which are mixing. One of those neutrinos have to be the electron neutrino because this is the one coming from the sun. The other one is the neutrino into which it is mixing, presumably mu-neutrino, but perhaps tau-neutrino. We don't know. But what we can do is analyze this by saying the effect is due to an electron neutrino oscillating into another neutrino of mass m2, and delta m squared is that mass difference. Now, I will go freely back and forth between mass and between delta m squared because I'm always assuming that although I don't know the masses of the 3 neutrinos, each one of them is much heavier than the next one. In other words, I'm always assuming that m2 squared minus m1 squared is approximately the same as m2 squared, and therefore I can just take the square root and derive a mass. And therefore I will move back and forth freely between plots versus delta m squared and plot versus m, which is all the plots I showed you today and in the last 2 lectures until this moment. The Kamiokande result is very similar. By itself, it is a similar picture, but when you put them on top of each other, you see something quite interesting, which is either good luck or bad luck, depending on your point of view. You see that although each one of them allows a horizontal region of almost any angle for a given mass, there is no overlap between the two. This is 2 standard deviation, and the overlap, officially speaking, is only this orange area, and the horizontal range is excluded. Now, here, I'm just presenting it as it is. This is the result of analysis of many different people, and at the level of 2 standard deviation, the horizontal region is excluded, but it is absolutely clear that if you take 2.5 or 3 standard deviation, what will happen is an emerging strip here which is allowed, and therefore don't completely write off that region, remember that this is still a possibility. When you take into account the galaxy results at the same level, you have a bigger margin of error because, first of all, the errors are still larger, and also the result is closer to the prediction of the standard solar model. You have to be inside this red area. And again, strangely, luckily or unluckily, by the time you take all three experiments, the overlap is very small. There are only two overlap regions, one here and one here. And both of them in mass are between 10 to the minus 6 and 10 to the in mass squared are between 10 to the minus 6, 10 to the minus 4, which means that the mass of the heavy neutrino into which the electron neutrino oscillates is between a milli-electron volt, the mass itself is 10 to the minus 3, and 10 milli-electron volt. And more precisely between really 2 and 5 milli-electron volt if you look at it. You also see that there are two solutions, one of almost full mixing, which theoretically is very unlikely. This is a mixing angle of maybe 30 or 40 degrees. Why should there be such a strong mixing angle? It would mean that the physical eigenstates are 50-50 combinations of electron neutrino and mu-neutrino. The other is sine squared 2 theta of 10 to the minus 2. And just for fun, you may remember that at the end of the lecture yesterday, I showed you a little game of numerology. I said, what would happen if the mixing angle of electron and muon will be simply the square root of E over mu, in the same way that the Cabibbo angle is the square root of D over S. If the mixing angle between the electron and the muon would be the square root of electron mass over muon mass, it would be here. So it is not at all far from this allowed region from the solar oscillation. But I want to repeat again and again. Formally speaking, at the level of 2 standard deviation, these are the only 2 allowed regions. But it is entirely possible that the correct solution is anywhere here, because this is within the galaxy experiment. It's on the boundary of Kamiokande and the boundary of Davis, and only a fool would insist that all of these experiments must be correct to 2 standard deviation and cannot be 2.5 standard deviation in at least one of them, which is all it takes. So these are the preferred regions, but it could still very well be somewhere in that range. Of course, it could also be here, etc., but that is the preferred region. What is more important is that all of these experiments are pointing to the general area between 10 to the minus 2 electron volt, I'm talking now in masses, and about, let's say, 10 to the minus 4, or a few 10 to the minus 4. To say it still in other words, milli-electron volt within 1 order of magnitude is the mass of the object into which the electron neutrino oscillates. So if all the solar puzzle depends on neutrino oscillations in matter, you immediately conclude that the electron neutrino is much lighter than a milli-electron volt, and the mu or the tau-neutrino, the one into which the electron oscillates in the sun, has to be of the order of milli-electron volt, give or take factor 10. That is already very, very important information. Remembering, of course, that it could be that the solar oscillation have nothing to do, the solar neutrinos have nothing to do with these matter oscillations, but that is another question. So now we are in position to try to summarize everything that we said so far. Here is the first graph that I showed you at the beginning of the first lecture, in which on one page we have the neutrino masses covering 15 orders of magnitude, the neutrino lifetimes covering orders of magnitude from 1 millisecond to the age of the universe, and the neutrino mixing angle coming from full mixing to very small mixing, which is much smaller than the smallest quark mixing angle. We started the series of lectures without knowing anything. The neutrinos could be anywhere from here down, not only to here, but much below it. And we are now much wiser because we learned quite a number of important things. What I show you here is a compendium of everything we've done in the last 2 lectures and in the first half of today's lecture, omitting all the red herrings and all the things that we analyzed and excluded. What we learned is the direct limits are nu tau, nu mu, nu e. We learned that the cosmological limit and the neutrino as a dark matter candidate would be here. we learned that with a very small probability, there might be a tiny region allowed here and here for the neutrinos, but it is very unlikely. So let us ignore this for a moment. This is where the 17 keV neutrino could have been, but isn't. The nu, mu, nu, tau oscillations, which are very important, exclude this range, which means that if the neutrino is dark matter or below, and if you are paying attention to this, then it has to be outside here. If it is exactly dark matter, it has to be on this black line and to the left of the blue line. The solar oscillation point at one of these two areas, or possibly somewhere here, and that's what we know. But this is considerable knowledge. This is much more than we knew a few years ago, and it immediately points at two regions of interest. One is this region, which has to be probed, and the other is this region for the dark matter, which has to be probed. And it immediately points at two major candidates. What would be nicer if this would be the mu-neutrino and this would be the tau-neutrino, and then you solve all your problems immediately. This is very optimistic, and of course there's an enormous number of experiments and theoretical problems to be discussed before you reach such a conclusions. But let me now move to the last phase of these lectures, to the analysis of different scenarios. Now, I remind you that in the first lecture, incidentally, everything I said until now has nothing to do with guesses about ratios of neutrino masses. We discussed in the first lecture what could be the ratio of the tau-neutrino to the mu-neutrino to the electron-neutrino mass. And I showed you this graph in which every line here is a decade, every line is a factor of 10. And it says that if the mu-neutrino is arbitrarily here, the tau-neutrino would be here if it is linearly related. Nu tau over nu mu is tau over mu. It would be here if it is quadratically related, like the seesaw formula. And it would be here if it is quadratically related, but not in proportional to the leptons, but in proportional to the top and charm quark, which is what grand unification would tell you. And you see that if the mu-neutrino is here, the tau-neutrino could be here or here or here. This is 20 times heavier. This is 300 times heavier, and this is 10,000 times heavier. So it is a very wide range, but still relative to the full 15 orders of magnitude, it is not such a wide range. It is only 3 orders of magnitude. And similarly for the electron neutrino. If the mu-neutrino is here, with these 3 versions, the electron neutrino would be somewhere below here. We will come back to these two when we discuss the different scenarios. So here we are with this map, which I will keep here now on the side. And I would like now to go through specific scenarios. The first scenario is what you might call neutrino at the limit. This is the favorite scenario of Glashow. It is the ugly possibility that the tau-neutrino is around 10 MeV, the mu-neutrino is around 200 keV, the electron-neutrino is around electron volt, and all of them are very near the direct experimental limit. It is extremely unlikely and extremely ugly. First of all, it requires new physics below 100 GeV. Let me go back and remind you of another picture that I showed you in the first lecture. When I explained the seesaw mechanism, I showed you this slide rule. I told you that if you know the mass of the neutrino and the mass of the normal Dirac particle, you can derive from it the scale of the new physics lambda that is driving this seesaw mechanism. And all you have to do there is to put a line on this graph, because the mass of the Dirac particle is the geometric mean between the neutrino mass and the scale of the new physics. And since this is logarithmic, a geometric means become arithmetic mean. Arithmetic mean simply means there's a straight line between the two. So now, if I want the tau-neutrino to be at 10 MeV, and the tau is here, it tells you that the level of new physics is below the mass of the W and the Z. You see? So it is a seesaw mechanism, but with a mass below the W and the Z. And this is something which is very, very suspicious and unattractive, because it would be kind of new physics that shows itself only with the neutrino right-handed mass and with no other piece of physics. This would also require a majoron. It would also require that the age of the universe is young, 10 to 11 billion years, which is somewhat unlikely, although not completely excluded. it would require that we ignore the primordial nucleosynthesis argument, which rejects that corner of the plot. It leads to other potential difficulties in astrophysics, which I don't have time to explain. And it provides no explanation for the solar neutrinos, because if the neutrinos are at these masses, this has nothing to do with the solar neutrino puzzle and with all the data I showed you. But worse than that, it has no redeeming features. It doesn't solve anything. It doesn't give us any benefits. That is not a reason why it is not true in nature, but all of this is very, very unlikely. However, to get rid of this possibility, you have to improve the direct measurements of masses, and also to improve something else I don't have time to discuss, and that is neutrinoless double beta decay, which probe electron masses, electron neutrino masses in the EV, in the electron volt range. So this is scenario number one. I consider it unlikely, ugly, but not yet ruled out with complete confidence. Scenario number two, I think, can be ruled out now, and that is the possibility that nu tau and nu mu are not at the limit, but they are in this no man's land between the limit and the cosmological dark matter region of 20 electron volt, such as the 17 keV or anything like this. This is forbidden, as we've seen, by combination of cosmology and particle physics. And now defunct 17 keV neutrino was a good example, because you could see, as I said yesterday, how ugly and dirty and concocted have to be the theories that would make it survive. So in that respect, it was a very good lesson. I would say that this no man's land is by now excluded. The third scenario is the favorite. If we say that neutrinos are not at this little window in the limit, and they are not in the no man's land, then the next possibility is that the heaviest neutrino is at the dark matter level, namely the tau-neutrino is around 20 electron volt, and nu tau is the cosmological dark matter. Then what can we say about nu tau over nu mu? Nu tau over nu mu could be 20 or 300 or 10,000, according to this picture that I showed you, that nice picture here. If it is 20, then 20 electron volt divided by 20, the mu-neutrino is 1 electron volt. If it is 300, it would be 10 to the minus 1 electron volt. In both of these cases, it would fall right in the place where the atmospheric neutrino results are obtained. But if it is 10,000, then the mu-neutrino will be 2 milli-electron volt, which is right at the range of the solar neutrino solution. So if we go back to my picture, summarizing everything, if I go back to my map, which summarizes everything, and I remind you that here is the cosmological dark matter and here is the solar neutrinos, and I put over it this thing, you see that if the mu-neutrino is responsible for the solar neutrino oscillations, then the tau-neutrino at the upper edge of the allowed region, this is the possibility of top squared over charm squared, is exactly at the position of the dark matter. So that looks very attractive and very hopeful. But there are problems. First of all, if you want to say that the tau-neutrino is at 20 electron volt and the mu-neutrino is at a few milli-electron volt, you go back to this slide rule and you start looking where it will be. So you now have to take the tau-neutrino at the dark matter, and the Dirac particle would be the top, and you end up around 10 to the 12 GeV, which is not grand unification. Grand unification is 10 to the 15, or these days 10 to the 16 GeV. So you have 4 or 5 orders of magnitude away from grand unification in this case. Now you say, all right, maybe there's some other physics. That's fine. But if there is some other physics, there's no reason to believe that the ratio is really given by m top over m charm, which was motivated by grand unification. So it's not absolutely clean and neat, and there is a problem here. Also, you cannot explain the experimental result on the atmospheric neutrino, which could still be wrong, could still have to be reanalyzed, but this is a problem. In any case, this is at least sufficiently favorite in order to study it seriously and to try to reach some conclusions, whether it is right or wrong, because it is one scenario which hangs on two handles, on the dark matter possibility for nu tau and on the solar for nu mu. It is interesting to see, however, back to the slide rule, that no matter what you do, you get into an area which is neither gun unification nor a low energy area. You see here, I put 4 different lines. If the tau-neutrino is the dark matter, and the Dirac particle is the top or the tau, I have these 2 lines. And if the mu-neutrino is responsible for the solar oscillation, and the Dirac particle is either charm or mu, I have these 2 lines. And in all 4 cases, you reach values which are between 10 to the 8 and 10 to the 12 GeV. You never reach the gun unification area, and you never reach the area of a few TeV where lower things could happen. Now, anything could still happen here. In particular, any of these ideas could happen here. But we certainly don't have a clear favorite theory with an intermediate energy scale, which is giving us some new physics. So this is food for thought. If scenario number 3, the favorite, is correct, then there has to be perhaps some new physics and intermediate scale below the gut scale. Scenario number 4, 5, and 6 we will go through very quickly. Scenario number 4 is, let us forget dark matter, insist that the mu-neutrino is responsible for the solar oscillation, which means that the mu-neutrino is at 3 milli-electron volt. And then the tau-neutrino could be the dark matter, but could also be only 20 or 300 times heavier, in which case it will be 1 electron volt or below, and the dark matter will have to be something else. That is definitely a possibility. Another possibility is that the solar neutrinos are accommodated by the tau-neutrino, that it is the tau-neutrino which is 3 milli-electron volt, and the mu-neutrino is much lighter, and the electron neutrino is much, much lighter. That means that lambda, the physics, the new scale of physics, is just right for gun unification. So maybe that is a possibility. I repeat, tau-neutrino responsible for solar oscillations, dark matter has nothing to do with neutrinos, and then the new scale of physics is at the gun unification. But then the mu and the electron neutrino are much, much below milli-electron volt, and probably we will never see them in any type of direct or indirect experiment. And finally, there is the possibility, which is unlikely, unnecessary, and unwanted, that all 3 neutrinos are below a milli-electron volt, and none of them have anything to do with anything that I discussed in these lectures. It cannot be ruled out. So altogether, 6 scenarios, but it is certainly sufficiently exciting to try to see the favorite one, and I'm going to devote the last 15 minutes that I have to the favorite scenario and how to test it experimentally and what to do about it theoretically. First of all, what is this scenario? The beauty of it is that it determines immediately a large number of parameters. Because remember, the neutrino sector has 3 neutrino masses and at least 3 mixing angles and some additional angles. It has many fundamental parameters of nature, none of which are known. And this scenario, if true, would give you that the tau-neutrino is around 20 electron volt. It is the cosmological dark matter, and it is in a range which is perfectly available for oscillation experiments in accelerators. It will say that the mu-neutrino is at a few milli-electron volt, and it explains solar neutrino. It will say that the electron neutrino is much, much lighter, much below micro-electron volt, perhaps a nano-electron volt or 10 to the minus 8 electron volt. It is too small for anything. It will never be seen. The mass will never be seen, and forget about direct attempts to see it. It will mean that sine squared 2 theta is probably order 10 to the minus 2, which is the left side solution of the solar oscillation. The solar oscillation has one mixing angle which is close to maximal, and one which is order 10 to the minus 2. This would be more likely. And if you really want to be cute, you would say that it's not very different from square root of ME over MU, but I remind you that this is pure numerology. Sine squared theta mu tau, you have no idea what it is, but on the basis of analogy to quark angles, you would guess that it is roundabout within an order of magnitude of 10 to the minus 3, and therefore could be accessible to experiments. More about this in a minute. This, of course, is wishful thinking. It could be much smaller, but this would be the first guess. It would be similar to the quark angle and accessible to oscillation. If this is the way the world is, I want you to stop for a moment in all of this technicality and just admire the beauty of it. What it would mean is that you will then do an accelerator experiment of nu tau oscillation in order to discover the cosmological dark matter of the universe, which is everywhere and which have been everywhere since the Big Bang. So that's one side of the equation. The other side is that you needed the sun to send us neutrinos to be detected in underground mines in order to determine the mass of the second neutrino, which is milli-electron volt. And in this way, you determine it to 9 orders of magnitude better than you could do by a direct experiment in an accelerator such as pi decay or k decay. So both of these things really boggle the mind, and they provide this beautiful marriage between astrophysics, cosmology, and particle physics, if all of this is true. How to test it? Experiments, experiments, experiments. First of all, general experiments, which are not specific to the favorite scenario, and that is still important to improve the direct limits, to get rid of the first unlikely scenario. It is still important to measure related decay modes to improve the knowledge of what we discussed yesterday about decays, decay modes such as mu to 3e and rare tau decays. It is still important for many reasons which have nothing to do with neutrinos to improve the knowledge of omega, the Hubble parameter, and the age of the universe, because they enter very strongly in all the cosmological limits. It is important to do neutrinoless double beta decay as long as the electron neutrino could still be in the electron volt range, possibility number 1. It is still important to do more accurate mu-neutrino, electron neutrino normal oscillation experiments in accelerators. It is very important to recheck the atmospheric neutrino experiment, because that really sticks out and that has to be cleared up. And it is, of course, important to search for other dark matter candidates which have nothing to do with neutrinos. And all of these things are things that should be done and go against the spirit of the favorite scenario. As far as the favorite scenario is concerned, there are only 3 large classes of experiments that have to be done. Most urgent is nu tau oscillations, which is a direct probe of a tau neutrino at the dark matter scale. Second is to do more and different solar neutrino experiments in order to improve the data and to make sure that the excluded region is excluded and that the preferred region is preferred, and that we really have a coherent picture from all different experiments. It will be very important eventually to introduce the energy dependence of the solar neutrino into the equation, because that can also be predicted, and once the measurements of the energy dependence are good enough, it can add information. So far, only Kamiokande tried to do it, but the data are not good enough for that. Future experiments will be able to do it. And finally, long baseline oscillation experiments could extend the standard information on neutrino oscillation from the present value of a fraction of electron volt another 1, 2, 3 orders of magnitude below, and eventually would cover this area which is presently empty between where the solar neutrinos reach, which is up to 10 to the minus 2 electron volt, and where the accelerator and reactor experiment reach, which is below, just below 1 electron volt. There are 2 orders of magnitude there that nobody can reach, and it would be nice to reach them, and this can be reached only by long baseline experiments, by taking the CERN beam and aiming it into Japan or Gran Sasso or Kamchatka or someplace. But the experiment which is most crucial, whether it's positive or negative, is of course the search for the dark matter. And the logic of it, which I already hinted at, I will repeat because I find this particular transparency perhaps the most clear and convincing of the whole story. It just goes step by step with logic which is very clear. It says, of all the dark matter candidates, the only one which surely exists is a neutrino. So let us first of all search for it. The heaviest neutrino is almost certainly tau-neutrino. If the tau-neutrino is the cosmological dark matter, we know its mass, it's 20 electron volt. The only way to look for such masses of tau-neutrino is oscillations. There's no other way. So forget direct measurements. We are 6 orders of magnitude below that. Oscillation with what? It is more accessible to oscillate tau-neutrinos into mu-neutrinos than into electrons because you have good mu-neutrino beams, and also because the mixing angle is likely to be larger because it's a mixing angle of neighboring generation and not of distant generation. So you want to do nu-mu, nu-tau oscillation. Therefore, the best way to search for cosmological dark matter for the time being is to look for nu-mu, nu-tau oscillation in an accelerator experiment, where the energy range of 20 electron volt is easily accessible, but you would like to improve the experiment in terms of the angle and not of the mass. So this is the experiment that you want to do, and that is going to be done very soon, twice at CERN. You are looking for mu-nu, tau-nu oscillations. You start with a standard accelerator beam of mu-neutrinos. You hope that they will oscillate to tau-neutrinos in the accelerator, and that fact by itself already will prove that the tau-neutrino is heavier than 1 electron volt, and it already proves that it is at least 5 or 10% of the mass of the cosmos. The mere fact that there is any kind of oscillations observed in an accelerator like CERN already means that at least 5 to 10% of the mass of the universe is tau-neutrinos. The tau-neutrino can only be discovered when it makes a tau, and the tau can only be discovered when it decays in any one of these ways. But of course, if you don't see the tau and you never see the tau-neutrino, you would see a mu-neutrino making a mu or a hadron, which is a very normal thing for charge current neutral currents, and also an electron, which can be done in several ways, although it is less normal. And therefore, this is the noise, and this is the signal. And there's also another background, which is honest-to-God tau, decaying in a proper way, but not produced from tau-neutrino and oscillation, but produced from other mechanism of tau production, and you have to make sure that doesn't exist. But fortunately, this is a small background. In order to improve the angle to the region that we talked about, you need at least 100,000 and hopefully 1 million events. And for that, you need a target which weighs of the order of 1 ton. And on the other hand, you would like to be sure that you have a tau beyond a doubt. And to be sure, absolutely beyond a doubt, you have to see the tau. And the tau lives a very short track because it has a lifetime of 10 to the minus 13 seconds, order of magnitude. And that short track is measured in hundreds of microns. And therefore, you need resolutions of perhaps 10 micron and a target of a ton. And then it is an old puzzle. What is it that weighs a ton and has a resolution of 10 microns? And the answer is, the only answer is the good old photographic emulsion in which our ancestors did experiments 50 years ago. Some of us also, not me. I came to the Weizmann Institute as a student to still see the microscopes looking at the emulsions, but they disappeared 1 year later. So I'm old enough to have seen a microscope looking into an emulsion. This is precisely what the Chorus collaboration is going to do here at CERN, and it's an extremely crucial experiment. There is the second experiment, NOMAD at CERN, which is doing the same except not looking at emulsion, doing it electronically and cleaning up the sample by kinematic cuts, which would presumably work faster, but on the other hand, if the signal is just a few events, would certainly be less convincing. But to have two experiments which complement each other would certainly be very beneficial, and these really are very, very crucial experiments. The last transparencies are the remaining issues. Theoretical issues are mainly three, but each one of them is a tall order. To understand the scale lambda, which is related to whatever we discover in the neutrino masses. To spend a lot of effort and a lot of ingenuity in studying the relationship between the masses and the angles, both in the quark sector, but now also in the neutrino sector. And the neutrinos can give you additional information. And finally, to understand the large-scale structure in the universe, something which is a necessary corollary for any candidate dark matter. If we are lucky and the tau-neutrino experiment here will discover oscillations, and the tau-neutrino is a good candidate for the dark matter, then somehow it has to make the large-scale structure of the universe. And that has to be understood. Experimental issues are divided between what you might call the old frontier and the new frontier. The old frontier are the direct measurements, the neutrinoless double beta decay, and the standard mu-e oscillation experiments in accelerators. All of this become completely useless if the tau-neutrino has a mass of the order of electron volt or 10 electron volt. But that has not been proven yet, and therefore all of these experiments are still useful as long as we couldn't prove scenario number 3, the favorite, or one of the scenarios which are below it. On the other hand, the new frontier is the new mu-nu tau oscillations, the solar experiments, repeating the atmospheric experiment, and the long baseline. All of this is physics below the dark matter line, below the 10, 20 electron volt line. That's where the action seems to be. And if anything positive is discovered in this, that immediately makes all of these experiments obsolete. And finally, neutrino physics is possibly, I would say probably, the best place in which we can observe physics which is beyond the standard model, because the moment you find one mass, or one mixing, or one oscillation, you're already beyond the standard model, you're already hinting at a new scale lambda, you're already connected it, and the beautiful connection between cosmology and particle physics is an added extra bonus to this whole field. Thank you very much.